Hi, and welcome back to my physics lecture video supplement series. Try saying that 10 times fast. Today I wanted to do a quick example using a ballistic pendulum. So usually how a ballistic pendulum works is you have an object that's fired at the pendulum and you measure the mass of the object, you measure the mass of the pendulum, and the change in height that the two swing to together, and from that you can get an initial speed of the object. So what I'm going to do is work through an example in which I know the initial mass of the projectile that's hitting the pendulum, I know the initial mass of the pendulum, and I know the change in height that the pendulum and object swing through together. I'm going to use that to figure out the initial speed of the projectile, and also the amount of energy that's lost by the projectile during the collision itself. So this is how you usually figure out the muzzle velocity of a gun. Well, it's a low-tech way of figuring out the muzzle velocity of a gun. Perhaps today, in the age of laser photodetectors, there are some more sophisticated methods, but this is a fairly tried and true method for doing this. So I have on the board a little drawing of basically a projectile, and it's going to collide with this pendulum bob. And I've labeled the projectile mass as mass projectile, MB for bullet, and it has some initial speed, V0B for initial speed of the bullet, and the pendulum has a mass of MP for mass of pendulum. And after the collision takes place, the two stick together and swing up to a final height, and so the height of the two ends up changing by some amount, delta H. And I've decided that I'm going to use a 70-gram brass ball bearing as my projectile, and a 115-gram pendulum for my pendulum. And I did this and came up with about an 8-centimeter change in height from start to finish. So what's the process that we go through in order to solve for the initial speed? So again, what we're looking for is the initial speed of the bullet, which is equivalent to the muzzle velocity, and what we're looking for is the change in energy for the system, which is essentially how much energy is lost from the point at which this bullet is fired to the point at which it's collided with this and they've swung up to their final position. So in order to solve this problem, we have actually two steps that we need to undertake. And the first is conservation of energy. So we need to, it's conservation of momentum. So we need to conserve momentum. So that means that our initial momentum needs to be equal to our final momentum. So if the initial and final momentum are equal, then that means that the mass of this guy times the initial velocity of this guy, which is the initial momentum of this system, has to be equal to the total mass of the ball and the pendulum together, because they're stuck together. So the total mass of ball and pendulum times whatever velocity they start off with right after the collision. So since they are stuck together, that means that their velocity will be the same. They move together, and therefore they have the same velocity as each other. So I can therefore solve for this initial velocity of the projectile in terms of this collision velocity. So I'm going to do that right now. And in fact, what I'm ultimately looking for is a speed, so I'm going to drop my vector notation and just solve for the speed. So this speed is going to be equal to the total of the mass divided by just the mass of the projectile times the collision speed, so the speed right after collision. So that's what I get out of conservation of momentum. The second thing that I need to use is conservation of energy. So I have to conserve energy. And the energy of the system, initially, we ignore. Everything before the collision we ignore because energy is not conserved in the collision itself. But as soon as the ball has actually collided with the pendulum, then I have some initial kinetic energy, and that has to be equal to the final potential energy of the system, because initially it's at its lowest height but fastest speed, and finally it's at its highest height and zero speed. So, and energy is conserved after the collision while it's swinging. Energy is in fact also conserved before the collision. It's only during the collision that we're really losing energy. So what that looks like is 1/2 of the total mass times the collision speed squared has to be equal to the total mass times the gravitational acceleration times the change in height. So that's conservation of energy as this thing is swinging. And since over here I've solved for the initial speed in terms of the collision speed, over here I should solve for the collision speed in terms of all this other stuff that's measurable. So to do that, I can divide both sides by this mass term, and since it's the same on both sides, it basically cancels out. And so then I can divide both sides by 1/2, which is the same as multiplying both sides by 2. So I have 2g delta h is equal to the speed after collision squared. So now I take a square root of both sides, and I get the collision speed. It's going to be square root of 2g delta h. So that also means that over here I can substitute square root of 2g delta h in for the collision speed. For what it's worth, if you use the numbers that I've obtained here, or that I started with here, really the one that you need is the change in height, and then g is 9.8 meters per second squared. So this collision speed, or speed right after collision, is going to be about 1.25 meters per second. Okay, so I'm going to actually write that up here just for fun, but we don't really need it any further. What we do need, though, is to plug in the masses of the projectile and of the pendulum and this change in height into this equation. And what we end up getting is that the approximate speed of the bullet before it hits the pendulum is 3.31 meters per second. So that actually solves the first part of the problem that we were looking for. So our muzzle velocity, as it were, is 3.31 meters per second. So that's the process for finding the muzzle velocity. Now what we want is to find the total energy lost by the system. So that basically means that we're looking for the energy of the ball before it hits this pendulum bob, and then the energy of the bob plus ball combined sometime after it's hit. So I'm going to use the initial energy, which is the energy just of the ball, and I'm going to use the final energy, which is the energy of the ball plus the bob together when they've reached their final stopping position at some height above where they started from. So what that looks like is that E naught is going to be 1/2 times the mass of the ball times the initial speed of the ball squared. So that's because all the energy right now is in the ball or in the bullet, and it's all kinetic energy. So using the 3.31 meters per second number that I found earlier and using the 70-gram mass of the ball, I come up with an initial energy of 0.383 joules. So now I've got to find the final energy of the system, which is the energy of the ball and pendulum together at some height. So E final is going to be total mass times G times the change in height that they've had. So this is 70 grams, this is 115 grams, this is 9.8 meters per second squared, and this is 8 centimeters. So that means that the final energy is approximately 0.073 joules. Excuse me. So now I want to define the change in energy. So my change in energy is just going to be this energy minus this energy. So 0.383 minus 0.073 means that I have a total of 0.310 joules. So 0.383 joules minus 0.073 joules gives me 0.310 joules. So that means that the amount of energy lost by the system is 0.310 joules. And what that energy is analogous to is if I fire my bullet into my pendulum or into my target, it has to deposit some amount of energy into deforming the target. In the case of the ballistic pendulum, there's usually some little rubber lining that can deform to sort of hold the ball secure. In the case of a gun, for example, that would basically be energy done to damaging whatever your target is. So you can see in this case quite a bit of the total energy was deposited into this thing's target. You can also do a follow-up calculation on your own of what would have happened if this thing passed through the pendulum bob, and you can measure how high the pendulum bob goes and so on, and figure out how much energy is then lost and therefore how much is then deposited. And that tells you why, for example, stopping power relies on the idea of a bullet actually stopping in its target. Not to mention that a bullet tends to be less safe if it actually goes all the way through its target, because it can hit something on the other side of it. So that's all I've got for today, and I hope that you've enjoyed watching, and I guess I'll see you next time. So farewell.